In this example, we consider xt is equal to e raised to power minus 80 times ut. That is, x of t is an exponential function, and we also impose a condition on this exponent a. A has to be a positive real number. And here we have plotted x of t. It starts from 1 at t is equal to 0, and then it exponentially decreases. And because of ut in this function, the values of this function are 0 on the negative time axis. In this example, we will not only compute the Fourier transform, but we will also discuss the convergence issues related to the computation of Fourier transforms. And we will relate to some properties of Fourier transform as well. Although we have not discussed the properties, but through this example, we will also try to relate with the Fourier series properties for the real-time periodic signals that we have already seen. Now, to compute the Fourier transform, all we have to do is we have to plug xt into this formula for the Fourier transform and work out the resulting integral. So let me just do this computation. Xj omega equal minus infinity to infinity e minus 80 times ut multiplied by e minus j omega t times dt. This ut, it will change the limits of this integration, and the new limits will go from 0 to infinity, e minus 80 e minus j omega t times dt. And then we can combine these two exponentials, 0 to infinity, e minus t a plus j omega times dt. Okay, it's a straightforward integral, e minus t a plus j omega divided by minus a plus j omega, and the limits goes from 0 to infinity. And then we substitute these limits in the numerator when we put t is equal to infinity. Because we have imposed this condition on a, the exponent is negative, and negative multiplied by infinity, the exponent becomes 0. And when we put t is equal to 0 in the exponent, the numerator becomes 1. So minus 1 divided by minus a plus j omega. So here we have it. The Fourier transform is 1 over a plus j omega. Yeah, but let's not just stop here. Let us see few other things from this example. So what we do, I multiply and divide the numerator and denominator with a minus j omega. So we get a divided by a square plus omega square plus j times minus omega divided by a square plus omega square. So because the Fourier transform of xt, it turned out to be a complex function in the frequency domain, in the frequency variable omega, we converted it into its Cartesian form. It has a real part, which is a divided by a square plus omega square, and it has an imaginary part, which is minus omega divided by a square plus omega square. And we can have an alternate form as well, where we have the magnitude of this function, magnitude of the Fourier transform, magnitude xc omega. We can very easily see that this magnitude is equal to 1 divided by a square plus omega square, and the phase or angle, it is tan inverse imaginary part divided by the real part, minus omega divided by A. So we have computed the real part and the imaginary part, and then the magnitude and the phase of the Fourier transform. And we can immediately notice that the real part of this function is an even function in omega, and the imaginary part of this function is an odd function in omega. Similarly, the magnitude is an even function in omega, and the phase is an odd function in omega. Because in these functions, if we, for example, in the magnitude function, if I replace omega by minus omega, then I will get the same right hand side, which means that magnitude of x j omega is equal to magnitude of x minus j omega, which satisfies the condition for a signal to be, for a function to be an even function. Now, let us plot the magnitude and the phase functions. So here we first plot the magnitude function. It's pretty straightforward to guess what the plot should be. At omega is equal to 0, the value of this function is maximum, and the value is 1 over a. And then for large values of omega, be it positive or negative, the magnitude decreases. And we get a plot like this. Similarly, if we plot the phase of this function, at omega is equal to 0, the phase is 0. At omega is equal to minus a, we get tan inverse minus 1, and tan inverse minus 1 is minus pi by 4. At omega is equal to a, we get minus pi by 4. And when omega increases, for large values, positive values of omega, tan inverse, it approaches minus pi by 2. And this minus pi by 2, it acts as an asymptote for this function. Similarly, at omega is equal to minus a, at omega is equal to minus a, we get tan inverse plus 1, and tan inverse plus 1 is pi by 4. And for large negative values, again the function approaches pi by 2. So if we plot this phase function, it will look like this. And from these plots, we can clearly see that the magnitude is an even function in variable omega, while the phase is an odd function in omega. In other words, xj omega is equal to x conjugate minus j omega. So xj omega is conjugate symmetric. Although we have not discussed the properties of Fourier transform, but if we try to relate it with the properties of Fourier series that we have already seen, x of t is a real function. And is it because that x of t is a real function we are getting the conjugate symmetry of the Fourier transform? Maybe, but it seems very likely that for real signals in time domain, their Fourier transforms should have conjugate symmetry, because we have already seen the properties of Fourier series and we can relate to that. However, when we discuss the properties of Fourier transform, we will clearly see what conditions should be on x of t for xc omega to be conjugate symmetric. Okay, now we come to the convergence issues. What if we remove this condition on A and if we allow A to take negative values? If this exponent A, it can, if the values of A can be negative, then when we compute this integral at t is equal to infinity, because one negative sign will be contributed by this negative A, at t is equal to infinity, the value becomes infinity and this integral simply does not exist. It just blows up. Why this happens? Because x of t, when a is less than 0, is not absolutely integrable. So for Fourier transform to exist, for Fourier transform to exist, x of t must be absolutely integrable.